So let's do a little example here. If we want to describe the loads acting at the cross-section C here, right there, we're going to start by sectioning the beam. Okay, so here we're going to divide this beam like this. Okay, so now we've got two different sections here. We want to find the internal resultant loadings at C. Now we can do that in two ways. We can look at the left side over here, or we can look at the right side over here, right? Which of those is going to be easier for us? Well, you want to look at what kind of unknown forces and loadings and moments you have on this beam. We've got a support force and a support moment here, right? That wall is acting on this. We don't know what those are. So it sure would be nice if we could avoid those, right? So we can use either section because they're both in static equilibrium. But it's going to be easier if we choose the unsupported section. So this is really only going to apply with cantilevered beams like this. But in this case, it's going to be easier for us to deal with the right section because we don't even need to know those support forces. Okay, so the first thing we're going to do is we're going to draw our sectioned beam. And so you can see we take this right section over here and we draw a free body diagram of it, right? It only shows the section of interest, just like we divided our potato in half. Okay, and so the plane that we divided this potato in half is this red line right here. Now, we're going to try to think about this section as an object in itself. We're going to ignore for a minute that it's connected to the beam here and that it's only part of the beam. And we're just going to treat it as a thing in itself. And we're going to solve the statics problem for that sectioned thing, for that sectioned beam. So our first question is let's figure out and name our forces, right? So we have this applied force right here. And we're going to have to find the magnitude of that force, and we're going to have to find where it's being applied. And then we have three coplanar resultant loadings. Okay, we have a shear force, a normal force, and a moment. Now these are all acting on this beam, and we can treat this sort of like a support force, right? You know, in a statics problem. In essence, this part of the beam is supporting this part of the beam. And the forces that it needs to use in order to support that beam are acting right here. And so we're going to try to solve for those three resultant forces. So our first step is to take that variable force and figure out where it's being applied. This is just like we do in statics if we had a variable force. So we find the magnitude of the force under the curve, right? So we think about, oh, okay, the area of this section here is going to be 180 Newton meters times our 6 meters. Times a half. That gives us the magnitude of that force. And then we're going to apply that through the centroid of our triangle, just like we did in statics. And so we get that nice 540 Newton force acting right there 2 meters from point C. Now again, we can go ahead and solve this as if this sectioned part were just an object in and of itself, okay, being supported by that other half of the beam. So we treat it as a statics problem. So we solve for the forces in the y direction, and we find that our V, our shear force, has to be equal to the only applied force, and so it's equal to 540. In the x direction, we don't have any forces acting, and so that one's easy. We don't have a normal resultant force there. And we find that we need a moment to counteract the moment created by this applied force. So we find the strength of the torque created by this 540 Newton applied force, and our moment, our internal resultant moment, is going to counteract that. And so we find that it's 1,080 Newton meters. So at the point C, our internal resultant loadings are a normal force of 0, a shear force of 540 newtons, and a bending moment of 1,080 Newton meters. So let's take a second to see if we can understand what these two resultant forces mean. So the positive shear force is the force that the left side of this beam is applying to the right side of the beam to hold it up. The applied force is pushing it down, or shear force is pushing it up, right? And so it's like that support force. But what's happening is that force is being applied internally here, right? The material right here is pushing up on this beam, okay? And so this is where we're going, right? In deformable bodies. We're going to start talking about the effects of that force on that material in there, because it's got to hold up all of that downward force of this applied force. The counterclockwise moment force is trying to counteract the moment created by this 540 Newton force. So this is trying to turn our beam in a clockwise direction. The moment internal loading is trying to keep it straight, right? So it's trying to turn it that way. So you think about this, if I push down on this, it's going to tend, point B is going to tend to go down, right? And this internal moment is trying to keep B where it is. And so that's the meaning of that shear force and that moment force. And both of those are going to put tremendous pressure on the material at point C, right? Because it's got that support force that normally would be over here in this wall is now just in the beam here. The left section is holding up the right section.